Okay. On behalf of the branch, I want to warmly welcome everyone to this technical session and general meeting. I think it's a good way to end the month of July, because in August, come August 20th, our formal inaugural ceremony will be taking place. So I think this is an opportunity to warmly invite everyone here today to join us at 10 a.m. 20th of August, where the national president in the person of Engineer Babagana will be formally conducting that ceremony. Other than that, as a branch, we are waxing stronger because of your support, and we are indeed very pleased to have you all in attendance today, and we hope that this session today will be a fruitful one for you. I think without much ado, I would like to invite my technical secretary, Engineer Dr. Akilu, to please welcome in our speaker today, Mostafa Nabawy, who is a Nigerian, but I'll allow him to explain why I call him my Nigerian brother. So over to you, Engineer Akilu, please.
Yes, thank you. Can everyone hear me? Yes, okay. So yes, this is a bio I pick a lot of interest in reading, because the speaker is currently sitting across me. He's a friend, a brother, a colleague. So the title of today's presentation is Jumping Spiders and Flying Bees, Enabling the Next Generation of Bio-Inspired Micro-Robots. Our presenter, like I said earlier, is Dr. Mostafa Nabawy. Mostafa is an innovative research leader in aerospace engineering with a sustained track record in researching aerodynamics, design of aerial vehicles, and biomechanics. He has contributed to numerous theoretical developments and engineering demonstration projects. In particular, Mostafa has extensive expertise in developing experimentally validated analytical models for fluid mechanics and micro actuation/sensing dynamics, and integration of these models into novel closed form design processes, allowing the development of efficient micro robots and microsystems. In his presentation today, Mostafa will share the innovative research conducted at the Microsystems Lab at the University of Manchester, aiming to understand how insect locomotion can help us design the next generation of microrobots, and how advanced engineering techniques can help us better understand insects' behavior. So yes, with that is by no means a representation of what Mostafa is. So that is a very modest bio. So I will allow Mostafa to proceed with his presentation. Like Obuk said, Mostafa is a Nigerian by induction, and I'll let all of you see that for yourself. Okay, so Mostafa, the floor is yours.
Can you please share so that I can share?
Yeah, I'm going to stop that now. Yeah.
While Mostafa is trying to share his screen, can I just let you know that if you have questions, please post it on the chat box, and at the end, Dr. Mostafa will respond. Just post your question on the chat box, and if your connection is very strong, then of course you can also speak. Thank you.
Okay, thank you so much, Obux. Thank you so much, Akilu. Thanks, a big thank you for the Nigerian Society of Engineers for the kind and generous invitation. It's a big pleasure for me to be with you today, guys, so thanks for that. And today I'll share a little bit of the research we do here in the University of Manchester within the Microsystem Research Group. Just before I start, I want to make sure, can you see my screen? Everything is fine and you can hear me, okay, great. Before I start, as Akilu mentioned, and Nigeria has a very special place in my heart, and I have personally lived in Nigeria for a couple of years when I was a kid, from the age of 5 till the age of 7. So to start up with, I have here some photos for you. I don't know. So the questions for you, this is a quiz for you guys. Like, where are these photos taken? So the easy answer is Nigeria, but I want the hard answer. Where in Nigeria?
Yankari Game Reserve.
Yes, that's correct. So so well done for that. So this was one of the trips I've done in the, like when I was there with my mother there, and you can see me beside some monkeys there as well. So that was a lovely time that I have never forgot in my life. I lived in Maiduguri, by the way, for the 2 years I lived there, and I went to school there, and I used to sing the national anthem every day, and I was a very efficient speaker of Hausa. However, I regret to say that over the time, I lost the ability to speak Hausa, which is something I really regret at the moment. And I'm also trying to convince Akilu to teach me again how to speak Hausa. But he's not doing a good job with me at the moment. So I was keen to say this background, and you can see even like I'm wearing today the Nigerian jersey. I didn't bring it for this meeting at all. I till now still buy the Nigerian jersey because I have like a strong, I would say, connection with Nigeria. And whenever the Nigerian football team is playing, I will always, support Nigeria to win. So it's when Akilu asked me to do this presentation, it was a no-brainer. I said, of course, that would be a big pleasure to speak to the society of engineers here, because Nigeria has a very, very special place in my heart. Okay, so I will go forward now with the presentation, just to give you a bit of like what we do in the Microsystems Lab. Our slogan basically in our research is small things, big ideas. So we are always working at the very micro scale, and lots of the time we are getting inspiration from nature. And when we speak about nature for robots and stuff, it's usually insects. So we are trying to do as much as we can to develop robotic insects. Obviously, at the moment, with the current levels of technology, there is a huge room for innovation there. However, to beat the performance that real insects can do is not an easy job at the moment. So I will share with you 2 examples today of what we do. One is the jumping spider. So this is the photo you are seeing here is for Kim, our very famous arachnid, who is a superstar, by the way, in every media at the moment, because we managed to train her to do jumps on demand, and I'll show you in a bit. And I'll also speak with you about like the work we are doing to develop robotic bees as well, getting inspiration from bees and trying to build like flying robots at the insect scale to fly using flapping wings. Okay, but before that, just a quick background about myself. Those are the things that I usually do in research. So I am an aerospace engineer, and I love and I have huge passion to aerodynamics, which is the science of like understanding how the airflow behave around bodies. And the most important body for any aerospace engineer is obviously the wing of an aircraft. So I have done lots of theoretical work, either in fixed wings or rotary wings or flap wings, as you can see from the figures here. And I've done also not just theoretical work, but also experimental work in wind tunnels and stuff. So we have something called the wind tunnel that we put a model of the aircraft inside and we start testing it. And we have also done innovative work in terms of building moving rigs, when you want to measure experimentally the aerodynamic performance. Is it okay? Okay. So when you want to measure experimentally the performance, the aerodynamic performance of like flapping wings, you need to move them in a medium. So we have built rigs like that, as the one you are seeing on the right-hand side. So this is just a CAD thing for it. Also, lots of work have been done in biomechanics. An example of that is the jumping spider that I'm going to show you today, and translating, not just understanding how insects work, but translating this knowledge into like, practice and application, engineering application, and trying to get something that is an engineered design. So this is a depiction of one of our robotic bees, basically. And I'll show you the real ones later in a video in this presentation. I've also had to finish my research expertise page. I have like good experience now with piezoelectricity. It originally started from my need to, when you want to build a robot like this, you need to have actuators, and one of the good candidates for that was piezoelectric actuators. So it started from this place. But later on, I started to develop this knowledge and this research stream into other things, like not just actuation, not just actuating robots, but also doing things like the one you are seeing here. This video is for a pump. It's a demonstration in the lab for a pump, which is basically it's a valveless pump. There is nothing more than a piezo diaphragm that is pushing the flow out, and these kinds of pumps are very useful in things of like applications like flow control. Also extended it to energy harvesting, which is a hot topic at the moment, and the way I'm doing it this way is basically creating flags which are very similar to like the flags that you would see any normal flag, but those flags have piezoelectric elements on top, and so they can generate electricity to, you know, power microsensors. And this is very important for applications like smart cities and places where they are really remote, and it's very hard to go and put sensors and change batteries there. So you can have energy harvester modules like those ones. So by this, I hope I didn't take lots of time, but just give you a little bit of a structure of like the different types of research. Not just myself, I'm doing it, of course, but all my colleagues in the microsystem research group, which I owe a lot in terms of what I've learned, and thanks a lot for the fantastic collaboration that we have been doing all over the year. So today I'm going to speak about more of like micro robots, and the question is, why micro robots? Why on earth do we want that? First of all, it is an area where there is huge potential for advancing our knowledge as humanity, because I always say smaller is stronger. Going smaller and smaller is always challenging. So there is nothing different in terms of the engineering concepts, but when you start going smaller, sometimes some of the physics as well change. And more importantly, the technological requirements becomes really, really hard. And just imagine, like, whenever you say, I'm going to do a robotic bee, I think this is interesting enough, you know? And it reminds you of things like Black Mirror, if you have watched Black Mirror, or like Eye in the Sky. And I'll show you some examples now. It's always like, you know, this looks like science fiction. And so our ability to create this science fiction in reality is very important. This is not just, you know, to advance knowledge and physics, but also for the applications that they can deliver. I will start now with the spider one. So this is a video for you to watch, and then we'll come back after it. Okay, I hope that was a good video. By the way, this video is available on the YouTube channel of the university, so if you would like to watch it on YouTube at any time, you can find it easily. And to be honest, you can find lots of videos for Kim. When we released this research, there was huge media uptake for this research, and I find like lots of channels have done other versions of Kim while she was jumping. And there are very interesting ones. If you just Google and write on Google, write Kim the jumping spider, you'll find lots there. So just to give you a quick overview about what we were trying to do here, we were trying to learn from spiders how to build better jumping micro robots. And it was a strain, and also at the other side, we would like to use engineering techniques to understand spider locomotion themselves. So it was a two-way research. It's not trying to learn from nature how we can do a better robots, and also trying to use the technology we have to understand how like jumping spiders do their job. So it was a very good collaboration between engineers and biologists, basically, so that the team was made of both sides. And we managed to use lots of the expertise we have and the facilities we have in the university to basically try to deliver some answers for the questions we have. So the first thing we did is basically we wanted to know the anatomy of the spiders really well. And we have here at the University of Manchester a very good CT scan facility, which is unique CT scan facility, I believe. Obviously, we are speaking here, the scale of Kim, we are speaking here of 1.5 centimeters. So it's very tiny, much, we are speaking of like very, very small part of your finger. So it's very, very tiny. And so to be able to get such details of all the body, all the legs, all the joints, and all of that, this is extraordinary. So this is, and it's really important for us because, as I'll show you later, we use this to do reconstruction of the biomechanics of the jump as well. The other thing, obviously, we started to train Kim to jump, and this was a very big challenge. Basically, we trained her to jump on demand without putting any food for her to jump for, because what we noticed that those spiders, they will eat like a cricket or so once per week. And we wanted, and if we just put a cricket for her to jump for her meal, that would not be sufficient for us in terms of the number of jumps we want to do. And more importantly, we will not be able to do the jumps at a very small, all the jumps at the same time interval. Because this is a biological system, Kim will change over time. She gains weight, she lays eggs, she does lots of things. So she's not the same Kim every day. And when you are speaking of insects, the time scales are very, all the lifespan of a spider is probably a year or so. Okay, so they are not like humans. So you need to be quick. So we managed to train her. We did like special tools to train her. And here, what you are seeing here are like high-speed cameras. So the speed of the camera, this camera was shooting with 3,200 frames per second. And such a jump will take milliseconds. Okay, what you are seeing here in slow motion, this happened in reality in milliseconds. In reality, when you see Kim jumping, you don't see her actually. Your eyes cannot catch that. You will just see that she was on that platform and she's now on the other platform. But what happened in between, you can never see it by your own eyes. And so you need such kind of very high-speed camera. And what we started to see is that she is doing jumping in a completely different way. So every challenge she is presented with, she will jump in a different philosophy. And this is what's telling you here. What we have done, like we have developed some mathematical models to compare her jumps to the optimum conditions. So there are two optimal conditions that you can work for when you jump. Either if you want to jump for the maximum distance, okay? So what you see here is the difference between the launch angle that Kim was using, like how she launches her body, the angle she launches her body with, compared to that optimum angle that will lead you to a maximum distance. Just to make it in a very simple terms, if you have a rocket, for example, and this rocket is like on a horizontal surface, and you want the rocket to go to the furthest distance, you launch it at a 45 degrees. That's well known. Okay, but if the platform is different and it's not level, then the angle will change. Okay, so what you can see, what I want you to look at here in this picture is where are the blue colors, because the blue color indicate where the deviation from Kim's angle of launch is minimum compared to the optimum angle. And you will find that when she was jumping like very far distance, either very far distance or very high distance, the ones that are very energetically demanding, she will adopt like a launch angle that will allow her to do such mission. However, remember that spiders are arachnids and they are predators. They jump to kill. They don't jump just to escape from either lives or just for locomotion. They will usually walk, and when they want to jump, they will jump to catch their prey. So whenever we give her any challenge at a smaller distance, smaller x and a lower z, if we compare those jumps with another optimum, there is another optimum which is basically minimum time to conduct a jump in the minimum amount of time, which basically means to be very fast to catch. You will find that all her jumps, the blue area here in the figure on the right, is now in the middle part and very close to like jump challenges that are, you know, either short or very easy for her. So basically she will adopt such kind of predatory technique of like jumping to allow the minimum amount of time for the jump so that she can manage to succeed in her kill. We obviously managed from those very high speed videos to, you know, track and trace all of the body points, the important body points and the joints of her legs. Okay, and what you are seeing here is how those angles and how those points vary over a jump. The previous one, this one was for her body angles, and here this is an example of some of the joints in her leg while she is moving. Okay, and this helps us machine learning modules and, you know, to try and learn better control strategies for our robots. So all of this helps us to data to be fed into, like, you know, appropriate engineering tools, either like machine learning, artificial intelligence, any kinds of methods that we use. This helps us to develop better, you know, control algorithms and understanding of what's going on. We can implement this into the robotics side. What you are seeing here, it was our very first prototype of a robot. Just to give you the scale, this is my finger on the left hand side. So this is the scale of the robot. So it looks big here, but in reality it's very, very tiny. And this was just like a mechanism to jump. There is no any robot, I would say, taking place here. Okay, our next iteration, we started to have actuated models. So this model was like jumping instead of using my finger, it was using the motor that's on it. And you can see it's much more stable. And our idea basically for those robots is that the target we set ourselves is that we would like to develop robots that are smart enough and fast enough to catch a fly. So this is how we would judge the success of our robots. And it's a very hard thing. Look, for example, we humans, it's very challenging for us to kill like flies by swatting. It takes you a good effort as a human. So to ask a robot to do that, it's not an easy job, because you need to have proper actuation, you need to have proper sensing, and you need to understand the environment beside you. The robot needs to understand the environment, plan the mission, execute the mission correctly, and ensure it is successful. So while it's very challenging, but it opens the door for lots of, like, you know, knowledge and lots of interesting engineering to take place. So that was my first example for today. My second example is about flying bees. Okay, so the second thing is basically the robotic platforms that we developed to create flapping wing motions and ultimately fly in the same way as an insect would fly. Here we do two things. We try to understand how do flapping wings in nature work, and also how we can make engineering systems at very small scale that can efficiently drive and control flapping wings. Something in the literature well known as the bee paradox. In the 1930s, two French mathematicians tried to, you know, apply normal aerodynamic theories on bees and see if they can fly, and they found that their wings are very tiny, really, for what's going on, and there is no way that they can fly with such aerodynamics. And it remained as the bee paradox for years and years, till like in the 1990s, when Charlie Ellington in Cambridge started to do his large, gigantic robotic insect, but simulating the same flow at the same, what we call the Reynolds number, and started to see something like that, a leading edge vortex. So those bees and those insects, operate their wings at high angles of attack. And by doing so, they create, because of the flapping wing motion, they create something called the leading edge vortex. This leading edge vortex allows the flow to reattach on the top surface of the wing, and so it doesn't stall. So Charlie Ellington, when he did that, he managed to find the ingredient, which is the leading edge vortex. But after we knew that there is a leading edge vortex, it took another 20 years or so for people to try to understand what is the leading edge vortex really doing. And we here at the University of Manchester, we had our contribution there. And what you are seeing on the right-hand side is a snapshot from New Scientist, citing one of our research here, when I used some of my mathematical modeling tools to explain how a bee can be born with such tiny wing. Because what we have managed to show is that those wings, the role of the leading edge vortex, it doesn't create another source of lift or anything, just allows the flow to reattach so that the wing never stalls. So you can operate at very high incidence. The wing can go with very high incidence without experiencing stall. I don't know if you understand what I mean by stall, but I'll try to show this in the next couple of slides. One way of you, if you want to try it yourself, is that, let's say if you are on a bike or so, and you put your hand in the direction of the air, you will start feeling the force. If you increase the angle of your hand, actually you will get no force, because basically the flow has separated from your hand. And so this is what we call stall. What bees can do is basically they can avoid such stall, so they can operate at high angles, and so they generate much higher lift forces. And this means that with their very tiny small wings, which are very compact inside, they can generate they are much efficient machines in force generation. We also do lots of numerical simulations, and the videos you're seeing here on the screen are for 3D and 2D motions of wings, where we can see exactly the vortex structures that gets created and understand them. We also do experiments. So this video here is showing you one of the rigs that we use, and we have force sensors. So here we are setting the thing, and we have motors that goes through gears and stuff, and it starts moving the wings inside the water tank. Here it's just moving it in a propeller fashion, but we also have mechanisms that can do this in a battery fashion to mimic exactly what flapping is doing. So this helps us, by doing such kind of experiments, we can exactly know the amount of forces. And also we have technique PIV, or particle image velocimetry, which allows us to see exactly the velocity contours around such wing motion. Either we use piezoelectric actuators or general small DC motors that we can operate in an alternating fashion. The problem is that the technology levels at the moment are not very good, and also they are driven by other needs. So to get a tailored motor or a tailored piezoelectric actuator for the needs, basically we need high power density actuators. This is a big challenge. Usually a robotic bee will have those systems that you are seeing here. We will have an energy source, usually a battery. This battery is feeding its power to an actuator, either a piezoelectric actuator or a DC motor. It can be an electromagnetic actuator as well, or new types of actuators. But to modulate the power flow from the battery to the actuator, we need an electronic circuit in between. Basically, this boosts the voltage and changes it from DC to AC, because it's a reciprocating motion. Also, those actuators usually do not have sufficient amount of motion at their tips, so we need to amplify their motion to translate into bigger flapping angles of the wings. So we need a transmission mechanism, and then the wings at the end. So what you are seeing here is a graphical depiction of the whole system. So it starts with the batteries that are connected. So those batteries on the sides are connected to the power electronic circuit. And this power electronic circuit operates the two piezoelectric actuators, which are those two golden rods, and those moves the wings in the required motion. And this is a real simulation of one of our models. It's not the real model, but it is a real simulation of what in reality. Okay, here is a real model of a DC motor that we are providing, and this is in very slow motion. So what you are seeing here is that with just two tiny micro DC motors, we are able to generate a very high flapping angle amplitude. And it's not just about flapping the wing back and forth, also Also, there is a hinge mechanism in there. So all of this, while it looks simple, it takes lots of time in terms of like development and understanding and making something that works. My next video will show you this prototype while it's flying, but sorry, it's flying with feather power. What you'll see in the next video is that it's flying with feather power, though there is no batteries, so there is a tether wire that's going to the motors, and it's uncontrolled flight. So at the moment we don't have a brain, so it will be more of a chaotic motion. But when we measure the forces that are generated, those forces are more than sufficient to create a lift force that is that is larger than its own weight. So here it is. This is also in slow motion. So if you take care, you will find that there is a wire coming from below, and this is the power wire that is giving the power to the. There is a safety line on top, but it's not carrying the. It's not carrying the beam. Obviously, here you are seeing it in slow motion. In reality, it's much faster than that. This actually gets me to the end of my presentation. I hope you find it a useful presentation, and I've managed to give you a little bit of a quick snapshot of what we do. And I hope it was good use of your time. Thank you so much for your listening.
Thank you very much, my Nigerian brother Mostafa. What a fascinating insight into your research interest. Very amazing. You know, I'm proud to have you on the same floor as myself. Now, if you can see the questions on the chat box, then there won't be need for me to read them out. But otherwise, I'm happy to read them out, depending on whichever one is convenient for you.
Okay, I will open the chat box. Yes. No, okay.
The first question starts from it was labeled Q1.
Yes. A fast-moving camera was used to capture the spider jump. How was the frame detection motion converted to the 2D image showing angle versus jump? So we had two cameras actually. We had two high-speed cameras, one from the side and one from the top. Okay. And then we managed, once you record those videos, you can take those videos into like motion tracking algorithms. We have some motion tracking algorithms, but I must also say that there are some open source software as well. So for example, one of them is called Tracker. And it's a very nice, if you just write Tracker on Google and download it, you will enjoy working with it a lot. So what you can upload those videos into such a software and start to, you know, track the points that you are interested in doing. In some experiments, we can put markers on top and use our motion capturing system. Some others we can't, such as the spider. It was very hard to put like a marker on top of the body of Kim. So we needed to have very crisp videos, and basically it was done manually. Basically, so tracing the points of the video manually using the tracking software. But also we managed to generate some automated software that can, for like specific features, but not all features of her body, of like the spider body, that are very clear and easy to detect. Those were tracked automatically using motion tracking algorithms that we have developed ourselves. So I hope this have clarified the answer. The other thing. We for the robots, by the way, it's much easier for the tracking because obviously the robot's not like a moving thing, and we have very tiny markers, some of them like 1 millimeter, just 1 millimeter markers that we can stick on top of the robots. And then we have a system of cameras, high motion, high speed cameras that basically capture the motion and tell us exactly how the wing is moving and things are moving. And this is very important when you want to develop control algorithms and stuff, because this helps you to do the feedback and basically manage to control the robot. In terms of pressure measurement, is there a correlation between the spider pressure in motion with humans? I'm not sure I understand the question. Like, how with humans? So the idea of the experiment was basically spiders. There is always this like open questions in spiders and tarantulas, arachnids in general, that what is the source of the force that they generate in their legs. They have muscles, but they also have fluids in their bodies, and they pump those fluids into their legs, and this helps to augment the force for them. The question then becomes, like, are they using muscles alone? Are they using fluids alone? Or are they using both? Because they have something that we don't have with the fluids, usually we'll say, of course, it's there because, you know, it will augment the thing. But our jumping spider measurements, just from the measurements of the power from that you can calculate, once you see those videos, you can calculate the velocity, the acceleration, the timing, and all of those things. And this helps you to calculate the kinetic energy, and from the kinetic energy, you can get the power. You find that the power levels of those jumping spiders, what we found is that the power levels of their jumps were actually can be delivered by just muscle power. So they really don't need the pressure. However, they have it. And I guess in, like, you know, accidental scenarios or so, they might be able to use it. But again, as I said, every species will have a different philosophy in their jump. And our job, I believe, as scientists, is to try to understand what each philosophy is and what is the best one to adopt for a specific application that we would like to realize. I don't know if this...
Sorry, Mostafa, before you take the next question, may I please ask you to take the question? It's not tagged, but could you take the question from Ganiat and Nifowoshe, considering that you've already answered 2 questions from Dr. Ezioke, and being conscious of time, please. So if you can take the question from Ganiat, it's just beneath the Q2 you just answered.
Okay. Going to the next question about, like, programming languages. Well, there is no specific programming language I would say we are using. We use everything in a way or another. But I must say that it's not really a programming language, but we can consider it so. We usually use MATLAB in general. That's because of the huge mathematical library that it contains, and MATLAB has developed over time significantly, and it's now very reliable. However, we use other things like Python, Fortran whenever needed. Obviously, in terms of CADing, we use SolidWorks mainly for that, but any CAD software can work there. In terms of tracking, motion tracking, stuff like that, usually this will be like a specific program coming for that. We sometimes need to do things in C# and C++, but I would say that the most of our work can be handled using MATLAB. So that's, I would say, the most used kind of program that we use. Then there is a question, is there any reason that a smaller battery was not used rather than the coin cell battery? Yes, coin cell batteries are not very good in terms of their power density. When I say power density, I mean by that the power to mass ratio or power to weight ratio. So the amount of power they deliver for the amount of mass they are is not that good. And to be honest, it's not just the power coin battery, it's most of the lithium polymer and lithium ion batteries. They are still not there yet. There are ideas, by the way, it doesn't have to be a battery. It can be also a capacitor. Like you can use a super capacitor or something to do that. One of the things that we are trying to do now is that I have some collaborations with Manchester. I don't know, guys, if you have heard about it before, but Manchester is the birthplace of a material called graphene. And when this material was discovered, they found lots of potential for it in different applications. And I had some collaboration with some of the guys from what we call the GEEK, or the Graphene Engineering Innovation Center. And we managed to prototype some batteries now that rely on some of the technology, not all of the technology of the graphene. The power has been boosted significantly, and we managed to do batteries that are less than 100 milligrams. So very tiny in weight and very suitable for what we are doing. And we tested them and they are operating well. So that's really good. So I would say in terms of like the propulsion system, the actuators, the batteries, we are on a good track. The biggest challenge then in the future would be the control and the brain, basically, to make those things happen in reality for sure. We can control things in the lab sometimes. We can have some controlled experiments using motion tracking and stuff, but that still remains in the lab. But to get like a robotic bee in your hand and just deploy it in the air, that will be hard. Obviously, if you deploy it in the open air with lots of gust and stuff, remember that they are very tiny. this is another layer of difficulty. So in indoors or like things that there is a very limited air speeds and no gas, it might be easier to operate. Okay, so lots of challenges to happen in the, that you need to solve. But I can see the future going to happen, if you know what I mean. Like, it is gonna happen. And I would say we here in the University of Manchester, we have started this like several years ago, and it's a stream that is driven by passion more than anything else. We want to make this happen. And I think usually the science that is relying on passion is usually a good science, because you have a very good motivation to do it.
Fantastic.
There is a question.
I think, Mostafa, sorry, I think the remaining questions, if we don't mind, are we okay to send these to the speaker via email? Because we're meant to transit into the general meeting from 6 o'clock, and I can see we're slightly above that. Thank you very much, Mostafa. If I can, I'll just share my screen to just see what we have next. May I please call on our General Secretary, Engineer Dr. Irene Okade, to please give vote of thanks to our speaker, please.
Thank you, Dr. Akilu.
Yes, can you hear me?
Yes, I can hear you. I can hear you as well.
Yes, sorry, if you can just give our speaker vote of thanks, please.
Okay, can you hear me? Can everyone hear me?
Yes, we can.
Oh, okay. Thank you very much, Dr. Mostafa, for your insightful presentation. And thanks for sharing your innovative research on jumping spiders. It's very interesting to hear about the anatomy of jumping spiders and how your team is using KIM to design micro robots. And thank you to all our participants who are here today. Thanks for your time. And with the permission of the speaker, we will upload the recording to our YouTube channel. So thank you, everyone. And we now bring the technical session to a close.
And just before people begin to log out from the technical session, if I could just make a few announcements and adverts. So, like I said earlier, this brings us to the end of our current theme, which is capacity building and innovation management. We're moving to our third theme, which will be safety, health, and environment. And so our presentation, our next technical session will be titled Protecting Our Collective Property. And this will be delivered by another colleague from the University of Manchester, Dr. Cecilia Medupin, who's from the Department of Earth and Environmental Sciences of the University of Manchester. So this will be the 27th of August, 2021 at the same time, UK and Nigerian time. Flyers will come out and we'll distribute this as through the usual platforms. So please make it a day with us again next month on the 27th. And just like you've seen now and always, I'm very sure you'd have a very swell time as well. So with that also, our sister branch in London, NSC London branch, will also be hosting their own technical session for the month of July tomorrow, the 31st at 2 p.m. And the title of their presentation will be Social Impact of Design Technology Education, Nigeria versus the United Kingdom. And this will be delivered by Mr. Ayodeji Alaka, BAMA, and who is the CEO of Osanimu Design. So please, if you have the time, the joining instructions and the registration links are shown on the screen. And please make it a date with NSC London branch. Thank you very much. And with this, we close the technical session, and we'll be transiting to the general meeting. Now, feel free to join us if you want, but technical session has ended, and you can always log out if you do not have if you cannot spare the next 45 minutes. Okay, thank you very much. And we officially draw the technical session to a close.
Okay. Mostafa, somebody was asking for your email address. I think there was an urgent request to link up with you. I don't know if you saw that message, so if you want to respond to that person directly, Mostafa.
So someone wants your email address. So is it okay to share? Yep. So Mostafa is happy for us to share his email address, and like I said earlier, we can also collate those questions that were not answered live, and we can pass them on to Mostafa, and he will